Hi there. Thanks for joining us for yet another episode of Space Nuts. This is a Q&A edition where we answer audience questions. My name's Andrew Dunkley, your host, and the questions today will revolve around black holes. In fact, not revolve around a black hole, go into one again. People seem to like to be spaghetti. We're also going to talk about planets around the TRAPPIST system, star collisions, and the early universe. So I hope you can stick around for this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Joining us, as always, is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Welcome to Space Nuts Q&A. Oh, no, you're not supposed to say that.
No, that's good. Welcome to Space Nuts Q&A, Fred.
Thank you.
Before we answer questions, we had a message sent in from Doug, and I thought I'd just play it in full because he brings up a point that I think probably went through to the keeper, which is an Australian term for we didn't talk about it. So, here's Doug.
Hi, guys. This is Doug Stone back from Boise, Idaho, and the Bruno Dune State Park Observatory and Planetarium. I may be wrong, but I was listening to your podcast back in 2019, number 162, which was the 50th anniversary episode of the Apollo 11 moonwalk. And you were mentioning the astronaut Bill Anders, who actually took the photograph, now called Earthrise. And I wasn't sure, I don't recall hearing it on your podcast, but are you aware of the fact that Bill Anders is no longer with us? Back in June of this year, he was killed in a plane crash that he was piloting off of the coast of Washington State. Again, I may be wrong. Maybe I missed it, but I listened to everyone. I don't recall you mentioning that. And I wanted you to know that so you can get that out to the rest of the space nutters. We show a really fabulous 30-minute video based on the Apollo 8 mission when that photograph was taken. It's called Earthrise, and if you haven't seen it, I strongly recommend it. We show it to our folks prior to our normal indoor presentation, which is 30 minutes prior to viewing there at the park. And if you haven't seen this, it's a real good backstory on that whole photograph called Earthrise. But that's all I got. More of a comment than a question. I do have some other questions, but I will have to get back to you. Thank you.
Thank you, Doug. That one was sent in late last year, and I'd overlooked it somehow, and I was digging around for questions the other day and found it and thought, oh, gosh, I meant to play that ages ago, so I thought I'd do a bit of catch-up, but appreciate that, Doug. William Anders, I didn't know, actually.
I did, because I talked about it on the radio show, but we didn't cover it. We didn't cover it in Space Nuts, probably just because there's so much, space news that we needed to cover. But yes, it was sad, the fact that Bill lost his life in a plane accident. I can't remember his age, but he would have been a good age, and of course, that Earthrise image, one of the iconic images of the space age, one that I guess everybody knows about. I'm intrigued by the video that Doug mentioned, though, and I will try and hunt that down. Video called Earthrise, which I think sounds well worth watching.
Absolutely true. Yeah, of course, that was an Apollo 8 mission.
Yes.
And when you go to NASA in Florida, you can look at the original layout of mission control for Apollo 8.
Yes, that's right.
It's fabulous.
We did that last
Absolutely.
year.
Yeah, isn't it terrific?
It is a real sense of, being there. Even the ashtrays on the desks are quite amazing.
Yeah, it is incredible. Yeah. Appreciate you sending that in, Doug. Now to a question, and this one comes from somebody who didn't tell us their name.
Hello again, guys. Thanks for an awesome podcast. I've been listening for over a year now, I think. Lo and behold, I have another question about black holes. Seems to be a topic that's recurring. So black holes, as we know, of course, nothing can escape them because you have to exceed the speed of light. Which brings me to the question, if something enters the black hole, like an electron or a proton or a grain of sand or whatever, does that object get accelerated to speeds above the speed of light before they hit the singularity? So if they enter at near the speed of light, will they get accelerated to speeds faster than the speed of light? That's my question. And also, I want to end with a joke. Why did the theory about dark energy not catch on at first? Because people thought it was repulsive. There we go. Thanks.
Wow. That was just so bad.
It's better. Yeah, it's better than our dad joke.
Yeah, it is, rather. Yeah, absolutely. I know you said you've sent in questions before, but sorry, I can't remember your name.
It's picking the voice. It's a familiar voice, and it's lovely to hear from you again.
Yes, indeed. Thanks for sending the question in. So, anything entering a black hole, electron, photon, anything like that, could it be accelerated beyond the speed of light? Is the basis of the question.
And it's a great question, but the bottom line is that even inside the event horizon of a black hole, the laws of physics hold, and speed of light cannot be exceeded. So what would happen is the gravitational pull of the singularity itself on the electron or whatever it is will basically, it will mess with its mass, if I can put it that way, because that's what happens when you're trying to accelerate things very close to the speed of light. Their mass gets greater. Now, the mass of the electron is one of the fundamental quantities of nature, but inside a black hole, all bets are off in that regard. But the speed of light is still sacrosanct.
Yeah. Nothing can go faster. So it doesn't mess with its mass, which makes it a massive mess.
A mass mess. I like that. Yes.
Yeah. Oh, no, it sounds too close to maths test.
Sorry. There's a bit, yeah.
I like that.
No, I don't like that either.
I found them very traumatic at school. I still can't believe we get so many questions about black holes, and more recently dark energy and dark matter, and anything that's got blackness around it seems to be flavor of the month when it comes to audience information. I suppose because these things are so mysterious.
Yeah, that's right. And they're all great questions as well, Andrew. None of the questions we get about these matters are ridiculous. They're always good questions. And yes, they're mysterious. They're at the cutting edge of research. We are baffled by what they are.
I like what you did there, matters that they bring to our attention. Yeah, it's very good. Let's go. Thanks for that question. Our next one comes from Dave. Hi, Andrew and Fred. Thank you for directing me to the article regarding Jupiter's rapid growth spurt. I noticed the article suggests that the same growth delay might have occurred with Uranus and Neptune, but they do not mention Saturn, which is interesting. I'm wondering why some solar systems, such as the TRAPPIST system, do not contain gas or ice giants. Were the gases not there in the first place, or has something occurred early in the expelled gas or planets from the system? Or have we simply not discovered them yet? Finally, is there a maximum limit to the amount of planets a solar system can produce and sustain? That comes from Dave in Inverell, New South Wales, Australia. I love this question.
It's a great question. The sort of musing about Saturn, that's a really good point. I'm not sure about the answer to that one. I would need to have a look.
We should just give it a ring and find out. That's horrible.
He's on fire, this guy.
Dear, oh dear.
But yeah, the TRAPPIST system. So gas giants and ice giants too, for that matter, form they form beyond the frost line of a solar system. And that's because there is, material, basically condensed water, it's ice, that is out there. And that, when it's secreted by protoplanets and planetesimals, that stuff makes for a very big object. It allows it to grow, and then the fact that it's growing and grows early enough in the history of that particular solar system that you've still got residual gas that can actually form around it. I think the TRAPPIST system, if I remember rightly, has planets that, yes, they're not gas giants, and I think it may be because all those planets exist well within the frost line of the TRAPPIST parent star. So any water vapor, any water molecules are going to be gas molecules rather than ice. Certainly wouldn't be water, because that can't exist in space. It just boils off.
Okay.
Sorry, go ahead.
No, I'm just saying, does this make the TRAPPIST system unique, or?
No, I don't think so. And sorry, it's Dave, isn't it? Dave's other comment about, are we just not finding the gas giants? I think that's unlikely, because they're the easiest ones to detect.
I was going to say that. Yeah.
Yeah. And,
I was going to say that.
Yeah. Well, you know that because you're a bright lad.
Would have been a lucky guess.
I think there are solar systems that consist of just sub-Earths, and in fact, we talked about one in the last episode, Barnard's star, which has got small planets. So it could be, it may well be just a quirk of the formation of that particular solar system. And in regard to Dave's last question, is there any limit to how many planets a solar system can form? Well, when you look at our solar system, yes, it's got 8 things that we define as planets, but then there's gazillions of other stuff. There's the debris, there's the asteroids, there's the dwarf planets, there's the asteroids, there's the trans-Neptunian objects, all of that stuff. So much material. There's the Oort cloud, all this material that's associated with the formation of the solar system. So there's probably no limit, but the limit is how many of those bits of stuff actually form into planets. And maybe the limiting factor on that is whether, once a planet's grown big enough, whether it can remain gravitationally stable with its peers, if I can put it that way, with the other planets in the solar system, or get kicked out. And that may have happened in the case of our solar system.
Yeah. Okay. We do see solar systems that have gas giants orbiting very close to their parent star.
Yes, that's right.
When we first discovered them, we thought, hang on, this is all weird.
Yeah.
But turns out we're more weird than they are.
Probably, yes. They're the hot Jupiters. That's right. Which may well have migrated from a position further out in their solar system and come in to the inner solar system.
I suppose the more we look and the more we find, the more we realise how each of these systems is probably unique.
In its own way, I think that's right. One thing I should try and check is what is the record known of number of planets known around an extra solar around another star. You might be able to check that.
I'm going to look now.
And I think the TRAPPIST system, which has 4, Barnard's star has 4 now confirmed. I think these are, the maximum almost the maximum numbers that we've discovered. I think there's at least one with 5 planets known. I don't think it extends to 6, but I might be wrong.
Yeah, let's see if we can find out.
Be a very good thing to do.
Depends if I could spell. Kepler 90 has 8 planets.
Right, there you go. Okay.
Yeah.
So, funnily enough, that matches our solar system.
Yes, so we're not unique anymore. We're just one of a pair. There's probably squillions, though, out there when you think about it.
Yeah, well, there's certainly, we think all stars have planets, so.
Yeah, or the vast majority,
The
probably.
vast majority, that's right.
Yes. All right. Thank you, Dave. Lovely to hear from you. This is Space Nuts, a Q&A edition with Andrew Dunkley and Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Our next question comes from Lloyd. He is in Cairns in far north Queensland. Very interesting, the episode about the neutron star collisions. You've spoken many times about black hole collisions and neutron star collisions, but do just everyday stars like our sun ever collide, and what do they create? Thanks for the show, Lloyd from Cairns. Yeah, it's a good question. And of course, we've got the upcoming merger and acquisition between the Andromeda and Milky Way galaxies, Milkometer.
Yeah.
And I've asked you the question as to, what sort of mayhem will occur? Will there be stars colliding? And you said basically not many, but possibly a few.
Yeah. So the normal thing would be 2 stars. If they were, approaching each other, they might basically end up orbiting around one another to become a binary system. Although we think the normal process is the other way around. But if you've got galaxies colliding, then that sort of interaction might become quite common. I think it's fairly rare for normal stars to collide because their masses are quite low. That means they've got a fairly small, if I can put it this way, gravitational sphere of influence. I mean, gravitational pull goes out to infinity, but it gets negligible beyond a certain distance. And so I think the bottom line with normal stars is they're not big enough to make, those attractive forces spread over a great enough distance, whereas black holes, neutron stars are. And it depends to some extent on the density of the environment as well. The environments within our galaxy that have the highest density of stars are the globular clusters in the middle. Stars, the star density is very high, but collisions are very rare.
Now that makes it a very good question, because I would have assumed it would happen more often.
Yeah,
than
the black holes.
Yeah,
yes, that's right.
So many more of them out there, but it's not the case by the sound of it. You mentioned binaries. Our sun, as you and I have discussed previously, was a binary. They haven't yet found the other one, have they?
No, that's right. I mean, it's a statistical thing. The likelihood is that it was part of a binary because more than 50% of all the stars in the galaxy are part of binary pairs, stars orbiting around each other. So we've lost our twin, and it might not have been a twin, but it wouldn't have been far off. It's perhaps one of the holy grails of what's called galactic archaeology, the study of stars in our neighborhood. And to understand the archaeology of the galaxy as a whole, one of the holy grails of that is to try and find a star whose chemistry exactly matches the sun. And there are one or two, but for various reasons, I think they've been ruled out as being our twins. Maybe they're too far away or something like that. I can't remember the details. But yes, one day we might find the twin of our sun.
Yeah, ours is a G-type.
It is
star,
yes.
which is not the most common, is it?
No, the M stars are, which are the red dwarfs.
Yeah, and you don't want to live there.
No, No.
No, we just got lucky enough to turn up next to a decent one.
Yeah, that's right.
Long lived and generally, calm.
Benign, yes.
Yes.
Right. Might be the other way around. Because of that, that's why we're here.
Yeah, I think you're probably right. Yes. All right, Lloyd, thank you so much for your question. I hope we adequately covered all your points.
0G, and I feel fine.
Space nuts.
Our final question today takes the form of a theory, I think. We'll let Mark explain.
Hello, guys. I'm Mark Rabelais from Baton Rouge, Louisiana, and I have a question dealing with the early universe. By the way, I love your show. It puts me to sleep every night in a good way. But I have a question about the early universe. I've been pondering this for a long time, and here's my chance to ask someone. I've seen the WMAP image of the early universe. If I remember right, that was of a time period approximately 300,000 years, maybe after the Big Bang. And of course, that image shows variations in the energy density of the early universe. And my question has to do with the image I have in my mind of the Big Bang occurring. And since the Big Bang was all that existed at the time, there could have been no outside influences. So the universe, all things being equal, at that time should have been perfectly evenly distributed. The mass should have been totally evenly distributed. Am I right? And which begs the question as to what caused the energy density fluctuations that the WMAP image shows. And my gut tells me, and this is probably well known, and I just, in my limited view, am not that aware of it, but is that due to quantum fluctuations? Is that the reigning theory? Anyhow, that's my question. What caused the fluctuations in the energy density in the early universe? I know it should be an easy question, right? Okay, guys. Thank you. Have a good evening.
Thank you, Mark. You too. I just looked up that image, the WMAP, and I know what he's talking about now. I've seen it before. It looks like an opal. Actually, it's got the shape and color and look of a beautiful opal, which they mine just up the road from here. The Lightning Ridge black opals, but quite a striking image. The Wilkinson microwave I can't say the word.
Anisotropy.
That's the word. Probe.
Yeah.
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 Go ahead.
Yeah. So let's do the context. You're absolutely right. The WMAP image is a map of the whole sky, showing the tiny temperature fluctuations that we record in microwaves, in the microwave spectrum. It was superseded about 15 years ago by the Planck image. So there have been three versions of this image. One produced in the 1990s by a spacecraft called COBE, Cosmic Background Explorer, the WMAP image, the Wilkinson Microwave Anisotropy Probe, and then Planck, which was the European Space Agency's version of the same thing. Each of them showed more detail, finer detail in this background with these extraordinary fluctuations. Mark is right in that what those fluctuations represent, what we're seeing is basically the glow of the universe when it was about 380,000 years old. So I call that map the cosmic wallpaper, Andrew. I'm sure I've said this before.
Yes, I recall.
Mainly because it's patterned like some wallpapers are, but mostly because it's behind everything we can see. Everything else in the universe is in front of that. So the cosmic wallpaper is right at the back, just as it is in a room. Everything's in front of it if you're in the room. So if you're in the universe, which most of us are, it's the cosmic wallpaper. So yes, those tiny temperature fluctuations come about because of essentially density changes in the plasma of the Big Bang, and in fact we interpret them as the effect of sound waves passing through the early universe. If you like, it's the bang of the Big Bang. We call them BAOs. Baryonic acoustic oscillations, and baryonic means normal material, something different from dark matter or dark energy. So they are, what we see is the reverberation of the Big Bang. But basically, Mark is right in questioning what the origin of those fluctuations were in the immediate aftermath of the Big Bang. Much earlier than 380,000 years. We're talking about 10 to the minus 32 of a second, which is a period we call inflation. It's when whatever mechanism did it, and we don't really understand what, it caused the universe to grow exponentially over a very short period of time, of the order of 10 to the minus 32 of a second. And indeed, Mark is correct. It is quantum fluctuations in that expansion that are thought to have led to the growth of structure, the structure that we see in the WMAP image, and also now, which we see as galaxies around us, and what we call the cosmic web, that those strings of galaxies, filaments of galaxies, and a kind of honeycomb of material that we see. So yeah, all kicked off by quantum fluctuations in the inflation field.
Well done, Mark. I remember us talking recently about how they've discovered all these connections between the supercluster groupings of galaxies, and the wider we view and the more we look, the more things are connected. It's quite extraordinary.
There's some new work that's just been published from the James Webb Telescope that we might cover in a future episode that suggests that galaxies in the universe, in the very distant universe, have a preferred direction of rotation.
Is that right?
And that is weird because we expect it to be random over the whole universe.
Yeah. Wow.
That's one that we might cover.
Yeah, that'd be a really good story. But fabulous question from Mark, and we appreciate him sending that in. It also reminds me, Fred, the other day I saw that story resurface in the media about our universe existing within a black hole. So that one's doing the rounds again.
That's right, and those two stories are interconnected because one of the possible interpretations of having galaxies that rotate in a particular way is that the universe is inside a black hole.
Yeah, that's just way too much for me to think about. I have enough trouble backing the car out of a garage.
Is your garage a black hole?
It can be. It can be.
Might be.
Yeah. A lot of them are these days. Yes. All right. Thank you, Mark. Thank you to everybody who sent in questions. We need some more. So if you'd like to send a question in to us, go to our website, spacenutspodcast.com or spacenuts.io, and just click on the AMA link at the top, which we still haven't been able to rename. So that's where you can send audio questions or text questions, and please tell us who you are and where you're from, because we just like to know so we can spam you. No, we don't do that. We don't do that. Hugh does that. Thanks to Hugh in the studio. I wondered how I'd get him today. That one worked. And we'll see you later, Fred. Thank you so much.
Great pleasure, Andrew. Always good to chat, and we'll see you next time.
We will indeed. Fred Watson, astronomer at large, and yes, thanks to Hugh in the studio. And from me, Andrew Dunkley, thanks for your company. We'll see you on the very next episode of Space Nuts. Until then, bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.